when dealing with collisions in two dimensions, some extra unknowns become apparent. So in this simple setup, we have object one. Imagine you're looking down on a pool table. Object one is moving towards object two. We have object two being stationary. So the initial speed of object two is 0, or initial velocity. The initial velocity of object one is just in the x direction. There's a collision. Object 2 moves off at some angle theta 2 at some velocity v2 final. And object 1, after the collision, moves off at some angle theta 1 at some velocity v1 final. And you can see it's in two dimensions. Both of the final velocities have some y component and they have some x component. Now momentum is a vector, which means that momentum has components. It has x, y, and z components, which means that the momentum has to be conserved in each dimension. Now, I'm not worried about the z dimension, out of the board or into the board. Just like on a pool table, right, a normal shot, the balls aren't going to fly up into the air or go down into the table. But here we have y direction up and down, x side to side, left to right. We're going to look at the conservation of momentum. So in the x-axis, before the collision, what's the total momentum of the system? Well, you have mass 1 here. You have the initial speed, or initial velocity, v1 initial, just in the x direction. Mass 2 is stationary, so it has no velocity, therefore it has no momentum. So the total initial momentum is just the momentum of the first object. After the collision, both objects are moving. Both objects have momentum. Now we have to worry about both objects. However, we're just interested in the x component of the momentum, which means that we're only interested in the x component of the velocity, right? The masses don't change. The masses are scalars. So the final momentum of object 1 depends on the mass of object 1, and the velocity of object 1 in the x direction. Well, if this is the velocity here of object 1, there is some x component to that velocity. This is angle theta 1, just like this is angle theta 1. So the velocity of object 1, the final velocity of object 1, times the cosine of that angle gives the x component of the velocity. Same thing with object 2. Mass 2 times the velocity of final velocity of object 2 times the cosine of angle theta 2. So you can see that in the two-dimensional case, we not only have the final velocities to deal with, we have the angles that they come off at. So rather than 6 unknowns, we now have 8 unknowns. In the y-axis, let's look at the momentum in the y-axis. Object 1 here has no y velocity. Therefore, it has no y momentum. Object 2 is stationary. It has no y velocity. Therefore, it has no y momentum. So the total momentum in the y-axis initially is 0. All of the momentum is initially is in the x direction. But after the collision, now these objects have some y momentum. Object 2 here, so this is v2 final. This is the horizontal. There is some component in the y direction. Well, if we know that this here is theta 2, this is the component in the y direction, that's the opposite side of that triangle. So we have to use sines instead of cosines. So it's the exact same setup as before, except sines instead of cosines. This is theta 1, and that's theta 2. One distinction. Your book has a plus sign here. It's just adding these momenta. But if you look carefully, M2, right, is going in the positive direction. M1 is going in the negative direction. In fact, I actually have these backwards. So M2 is going to have some positive momentum. M1 here is going to have some negative momentum. These things have to add to 0. So since I define downwards to be negative, M1 is going to have some components in the negative y direction, That's the component of its velocity. Therefore, the component of its momentum is going to be negative. So if you don't plug that in, if you use the angles as shown here, you'll get a wrong answer. You'll get two positive numbers when added together that won't equal 0. So be careful when you're doing these conservation of linear momentum problems that you look to see and define the momentum appropriately. If an object is moving to the right, it has some positive x momentum. If it's moving to the left, it has some component negative x momentum. If some component is moving up, it has positive y momentum. If some component is moving down, it has negative y momentum. And finally, so we have two equations here, one for the x direction, one for the y direction. And then finally, we can also look at if this is an elastic collision, we can actually talk about the conservation of kinetic energy and how kinetic energy is conserved. Now, kinetic energy doesn't have an x component or a y component. Kinetic energy is just it's a scalar. So this has some kinetic energy, 1/2 m1 v1 initial squared. This has no initial kinetic energy because it has no speed. This has some speed v2 final. This has some speed v1 final. Square that, multiply by the masses, divide by 2 to get the kinetic energy. You can only use one kinetic energy equation. You do not want to break the kinetic energy up into components because it's a scalar, it is not a vector. Now, one additional change is your book for these equations. I have v1 initial shown and v2 final, v1 final. I use final and initial. Your book uses a prime number rather than v1 final. Your book will say v1 and put a prime there to distinguish between before and after the collision. I'm not a big fan of that notation. That's why I explicitly state final and initial. But just note that your book and I disagree slightly with notation, but they're the same equations.